Okay, my dear student, as we discussed before, that we have linear PDEs, and that linear PDEs can be solved using the domain decomposition method. And in previous lectures, if you revise all the lectures, in all that lectures, we discussed the domain decomposition method and the detailed treatment of the domain decomposition method with the linear uh, PDEs and non-linear ODEs. So here in this book, this is the book of Abdul Majid was, and this is already uploaded in your on your ERP, and you can easily download this book, and this is freely also available on Google as well. So if you look at this uh, portion, homogeneous heat equation, so first of all you need to know that what is exactly the homogeneous boundary conditions. So here the homogeneous boundary conditions are those kind of boundary conditions in which the these boundary conditions, when they equal zero, exactly this one, u of 0 of t is equal to 0 and u of pi of t is equal to 0. When these two boundary conditions are 0, then you can say they are homogeneous boundary conditions. And you can say this, you can see here, this is exactly the initial condition for the above heat equation, and this is exactly the heat equations. Partial u by partial t is equal to partial square u by partial x square, where x is in between 0 and t, where t is time and greater than 0. So this is exactly the homogeneous equations, and this was also the assignment if you revise the lectures. So this was the assignment in your previous lectures. So how you can calculate or how you can solve this heat equations using the domain decomposition method. So exactly in this book, each and every step is given, the solution and the whole treatment and the whole calculation is exactly uh, step by step. You can see in this book that they solve this equation using the domain decomposition method. So what uh, in first step they are choosing the operator from the above equation. So uh, the operator for the above equation can be written in this form: L of t of the function u of x t is equal to the operator x, or the linear operator x of the function u, which is depending on x and t. So this is exactly the first step of the domain decomposition method. What we are doing after this step, you are choosing, or we assume that this operator is invertible operator, and the inverse of this operator is exact. So applying the inverse operator L of t minus 1 to both sides of the above equation, and using the initial condition we find. Uh, so once you apply the inverse operator on this equation, L inverse, or and this inverse operator should be in terms of t, not in terms of x. So the because we are choosing the operator in L of t, so the inverse operator must be in this form as well. So once we apply this inverse operator on both sides of this above equation, then this equation reduced to exactly this form, and this is the, you can say, the uh, zeroth order solution. You can say this is for the domain decomposition method. So once you apply these inverse operator, and we also assume that these are invertible, so they vanished, and they gives you the identity, you can say vector, or the identity element. So then u of xt is equal to, and this sine of x is the zeroth order solution plus lt of inverse of this function. So in next step we define that, or we assume that that u of x, for this u of x, for the unknown function u of xt, the series form is exist, or we define this unknown function in a series form. And you can see here this one unknown function is equal to, or we assume that this is equal to the series of un of xt. So in next step we also substituting this one in the above equation. So the above equation 3.22 reduced to this form in series form. So this is exactly now the series form of the above equation. Now this series form can be written in this form as well, because we are expanding this series u naught plus u1 plus u2 up to infinity, the zeroth order function, or the solution of the zero order function, plus the invertible operator into the linear operator in terms of x, and the expansion of this series. You can see here this is expanded in this case. Now from this equation we identify the zeroth order solution, or the zero order equation for the heat equation. So u naught is exactly equal to, you can see here this u naught is the zeroth order form of the domain decomposition method, which is equal to exactly this one, and all other terms can be calculated from this series. And once you apply the nonlinear operator on the zeroth order solution, so what we are doing here, we exactly in the next term, if you want to calculate this u1, so for this u1 we are exactly, we um, will integrate the sine x with respect to t. This will be integral sine x dt, and the boundary condition which starts from 0 to t, I think so. So you can see here this is exactly this one. u1 has this form, integral sine x dt. So this is constant, and the integral of dt is t in this case, and this is exactly negative when you apply the boundary condition. So once you calculate all the terms u2 u3, so you will have exactly this form. And when you plug in all the values of u0 u1 u2, then you will have exactly this form, this equation. This is exactly the one solution of the above heat equation. So to solve these equations using the Edomian method, you first of all you need to know the that what is exactly the homogeneous boundary condition, and what are the inhomogeneous boundary conditions. So these are the, the topic from your BSc mathematics. So you need to know these sort of things from your uh, mathematical techniques books, you can see here. So this is another example, and you can see here uh, one thing for inhomogeneous boundary conditions is that if you have another function here f of, which is, for example, for instance, if we say, if there is another function which is f of x, and that f of x can be x plus cos x, or sin x, or tangent x, so then we can say that, and these boundaries are non-zero, then you can say that the whole scenario is inhomogeneous, or the heat equation is inhomogeneous heat equation. So but here in this case there is no extra functions, so we have the only function which is u of t is equal to u partial u square by partial x square. So this is again a homogeneous heat equations, and you can easily solve this equation using the same treatment. The treatment is, first you need to um, identify the linear operator, and then for that linear operator you need to assume the invertible operator, and once you choose the invertible operators, apply the whole invertible operator on the whole equation, so then you will have an equations, and that equations can then be transformed to a series form, and then step by step you can calculate the each segment of the equations, and once you calculate each segment of the equations, then easily plug in all segments in the series, and from that series, once you simplify, you will have the solution of this heat equation. So this is exactly the main treatment, that how you can calculate the domain decomposition method. So uh, try to read this book as well, each examples, and the video, the recorded video, and if you have, again still if you have any questions, query, then we can uh, also uh, uh, set a Microsoft meeting, a class, online class, and in online class we can also discuss each and every questions, and we can again calculate all these things. Thank you.